Roll out the latest episode of the IBM Qiskit Live Quantum Seminar Series dedicated to the research and academic quantum communities. Today, I am your host, Zlatko Minev from IBM Quantum Research, and I have the pleasure of hosting Professor Vladimir Manucharyan from the University of Maryland and the Joint Quantum Institute. Hello, Vladimir. How are you today?
Hi, Zlatko. Great. Thanks for having me.
Yeah, it's good to see you. Alas, this time we have to do it virtually, but it's a pleasure to have you. And where are you tuning in from today?
It's College Park, Maryland, about 17 miles from the White House.
17, exactly. Well, that's great. Before we pull up your slides, I'll give a bit of your bio. Vladimir received his bachelor in 2003 from the Moscow Institute of Physics and Technology, PhysTech, and his Ph.D. in 2012 from Yale University from the group of Michel Devoret. Vladimir was a junior fellow of the Society of Fellows of Harvard University during the 2010 to 2013. And he is also the recipient of many, many awards and recognitions and accolades, including the Sloan, the NSF Career, the DARPA Young Investigator, DOE Early Career, Google Research Faculty, and so on. So with that, it's my pleasure to turn it over to Vlad. Please take it away for us.
Thank you. Okay, so, well, it's a great pleasure to speak at this very popular seminar. Today I'm going to introduce to you a somewhat unusual for a circuit QED topic. I will try to kind of marry it to physics of strongly correlated systems. Hence the mysterious title. We will debug it a little towards the talk, and my talk will really consist of a bunch of introductions at very different levels to very different topics, and you're welcome to punch me with questions sort of at any level. So before I begin, let me thank my group and our funding sources. So our group is called Superconducting Circuits. That's our little brand logo. And this picture was taken, late in 2019, the last time we had a chance to actually gather up like this. As everyone else, we have not been allowed to do this ever since. So since that time, quite a few people have left to their greater future. And I thank them all for their contributions to this project that I'm about to describe. So, multimode cavity quantum electrodynamics is basically you take a Fabry-Perot cavity, some space isolated by two mirrors you see on the left and on the right, and in the simplest case, you're going to get succession of modes. The mode number one would correspond to the electric field profile like this, and then mode number two will have sort of the first one is half wavelengths, the second is full wavelengths, etc., etc. And then the frequency of these modes will be equally spaced by the spacing delta, which is given by the size of this, by the length of the Fabry-Perot and the speed of light. And this must be a familiar concept to many. If we couple a qubit to this kind of system, well, there's a great book which explains how this works, but I will walk you through the basics. So suppose the qubit excited state's energy E is just about matching the energy of the having one photon in mode K. So then the two will interact, and there will be what's called a vacuum Rabi splitting, and the two split states, they correspond to kind of equal superpositions, but with different signs or phases, where you have a photon in the K mode and qubit in the ground state, or no photon in the K mode, but qubit is in the excited state. And yeah, the Usually this is described by this kind of Hamiltonian where you have some modes of the Fabry-Perot. So a K dagger creates one photon in mode K, a K annihilates a photon in mode K, and the qubit can be represented as a spin. So there's a sigma z is the Pauli operator. So sigma z times G is basically minus G, and sigma z times E is plus E. And the coupling to the modes goes like this. So you form some kind of a position coordinate operator, AK plus AK dagger, and then it's coupled to the operator that is something other than sigma z, let's say sigma x. And for different mode, the coupling could be different, so we call them GK. Now, suppose I can tune the qubit frequency omega z. I use the kind of NMR notations. Suppose I tune it to the mode k minus 1. Well, then I'm going to form some superpositions with the mode k minus 1, more or less ignoring the mode k. And likewise, I can tune to mode k minus 2. And then I'm going to form superpositions with the mode k minus 2, etc. So this is really the life with multimode cavity QED when the coupling of a qubit to these modes is sufficiently weak. So in this case, you can guess that the coupling is, the coupling constants G are smaller than not only the frequency of these modes, but also the spacing delta between these modes. And this regime is very well described in this book. In fact, it brings a lot of interesting quantum optics phenomena and facilitates quantum computing. So today, though, I want to discuss many body states of radiation in multimode cavity QED. And that's an interesting question. So many body usually comes up a lot in condensed matter context. It also does come up a lot now in a quantum computing context because basically the quantum computer is needed to solve many body problems. So what is what is many body states of radiation? Let's use example of this Fabry-Perot. Well, if I just put one photon in mode K, that doesn't look like a many body state. But if I put a lot of photons in mode K, that is not gonna look like a many body state either, because our intuition tells us that if I put a lot of photons into my system, it's got to become classical, and that's not what we're up to. We want to discuss quantum many body effects, and so let me give you just an example of these many body states, and you're welcome to actually begin to ask questions at this stage, because as far as I know, this topic has been very scarcely discussed in the literature. So let's restrict the energy of these many body states to the energy of one photon in mode K. What other states we can compose that have the same energy? Well, let's use two photons, and let's put one in mode k minus 1 and the other in mode 1. So then the total energy of that state would be equal to the energy of the one photon in mode k. And then I have a number of options to do this. I can use k minus 1 1, but I can also use k minus 2 2. And in fact, there is of order of big O of k. Basically, it's strictly speaking in this case it's about k over 2 of such states that would involve two photons in the system, and they will be resonant with the k state. I can go further, and I can say, well, suppose I'm going to use three photons. And now, well, I'm just showing, I guess, one option on this plot. So I can put one photon in k minus 2, but then two photons into 1. And that also has energy that corresponds to one photon in mode k. And the number of combinations with three photons is going to scale as k squared. Use it as an exercise to compute an exact prefactor. And you can probably guess that as I introduce the 4 photon states, I'm going to get about k to the 3 states, etc. And it's very easy to convince yourself that if I consider a Fabry-Perot resonator, I consider a state, and I consider all possible energy states with k equals 100, and just 5 photons in the system, there will be 1 million degenerate states. 1 million degenerate states that have energy that corresponds to 1 photon at a frequency k. If the states are not really coupled to each other in any way, then we just don't care about them. But what if they are? Then a classical computer will be in trouble in calculating this, and that becomes precisely the kind of a hard problem in quantum mechanics, because it requires a large Hilbert space, even though there's not that much energy in the system. There's, we're talking about 5 quanta at most. And what I'm going to tell you today is that it turns out that if you place a single atom, but not any atom, the right one, that's exactly what it's going to do. It's going to couple a large number of these, maybe not all of them, but a large enough subset of these degenerate states to each other, and hence induce what is usually called a quantum many-body dynamics of radiation.
Mm-hmm. Quick question, but maybe
questions.
Here? Yes, thank you. This is very nice, very nice introduction. I guess here we want to maybe this is implicit, but yeah, we if the coupling is all linear, then you don't have any problems. I guess it's only when you have third order and higher couplings that you're going to be running into simulation problems, right?
Coupling, you mean coupling like here? This one? No, we're talking about this kind of coupling.
Yeah, yes. You need the atom in there. Mm-hmm. If you have a scattering or an impurity, that's classical.
Right. So yeah. Let me spell it out. So we're not going to consider a coupling any different from this one in terms of, I mean, you can call it linear coupling, right? In some sense, because you take a linear field operator and you multiply it by the qubit operator. Usually it's called linear coupling. It's a good question whether this is a good idea to call it like this. But probably what you're saying is that if I only restrict myself to 1 photon state, like in this example, or maybe it's better to say 1 quanta states, because qubits, some people like me prefer to consider qubit, excitation of a qubit as also a photon. Some people don't like that. But as long as there's only 1 quanta of excitations, then of course the total number of states that you need, let's say to model this cavity, would be k, right? Or maybe you want to take like 2k or something like this. And that's not a big deal, because we're talking about a Fabry-Perot with, let's say, a k of 100. But if you, for some reason, if your dynamics involves the states involving 2 photons or 3 photons, you're going to quickly run into troubles. In some sense, your modeling the system will be basically as hard as modeling complex molecules, because you're going to need an enormous Hilbert space to do it, numerically accurately, or you need to come up with some very ingenious approximation which just selects only a handful of these multi-photon states that are actually interacting, which is usually, that's basically the job of condensed matter physics, many-body physics theory, to find efficient approximations. But in some cases they just don't exist, and this is really why Feynman introduced the concept of a quantum computer. Is that, well, in some cases your dynamics just involves a large Hilbert space, and there's nothing you can do. Okay.
Thank you.
Any more questions just on this kind of very abstract introduction? At this stage, it could have been just a cavity QED. It doesn't even need to be circuit QED.
No, I think
right. So one thing you can sort of, yeah, okay. So one thing you can guess right away is that if the coupling to each mode is much weaker than the mode spacing, probably none of this is going to happen, which is probably why you never heard of this, at least in the context of cavity QED. That's a hint. So we need to get interactions right. It's not as bad for all possible parameters. So, and I can tell you right away that this situation is impossible in cavity QED, but it is possible in circuit QED. So now let's discuss a little bit the introduction to circuit QED. It's going to be my very brief and subjective one. Sorry, not a historical one. I'm just trying to get up to speed, people who don't deal with circuits that much, because my talk is actually going to be about circuits. So you can view superconducting, well, okay, here, quantum computer, pasted the slide from another talk, I'm sorry. In any case, you can view sort of circuit QED as some kind of a Lego game where you have a capacitor whose energy is quadratic in its charge. The capacitor C energy is a Q square over 2C. You can have an inductor, and the energy of the inductor is quadratic in flux. So for inductance L, the energy will be phi square over 2L. We don't really do resistors that much, at least not the ones you buy from radio shops, because we don't want uncontrolled dissipation. And then we have this Josephson junction, which is two superconducting qubits is what a transistor is to classical bits. And it's this sandwich of two aluminum films separated by a thin layer of aluminum oxide. There's quite a beautiful superconductivity physics going on, which you can reduce to just some electrical engineering description of this cross element, which goes like this. You introduce a mysterious variable phi, which is called the superconducting phase of the condensate of Cooper pairs. And then the derivative of this phase in time multiplied by flux quantum is voltage, which draws analogy to flux in the inductor, because the derivative of flux with respect to time is also voltage across the inductor. You say, well, maybe I just have an inductor. And you can say so, except that its energy is not quadratic in this flux, but it's a cosine. So it's a nonlinear inductor. But if you linearize it, you can define the linearized inductance Lj, which is the flux quantum squared divided by Ej, where Ej is the Josephson energy, just some property of this junction. And with no dissipation and with strong nonlinearity, the quantization of the circuits goes like this. You say that flux is a position and charge is momentum, and they commute just the same way. In fact, their product has units of h bar, and that's basically how we go. And with enough capacitors, inductors, Josephson junction, and imagination, you can think of producing rather complicated quantum dynamics. I like to say that you can produce anything you want. I can't really prove it, but it's also very hard to prove me wrong. Okay, now I need to introduce you to two more specialized notions. So one is all the Josephson plasma mode, which is this. So when you just take a Josephson junction, not only it has this Josephson nonlinear inductance, but it also has a capacitance due to the oxide. There's basic electric field in the oxide, and well, the plasma mode is basically oscillations of currents and voltages in this LC oscillator. It just looks like a Josephson potential here, and then at the bottom of it, there's some vibrations of phase. An interesting observation is that the frequency of this oscillation goes as product of 1/√of Lj Cj, and the capacitance grows with area, but inductance actually drops with area because it's 1 over the Josephson energy, and energy grows with area. And so the product becomes really just a property of the oxide, and that gives the frequency, that's called plasma frequency, about 20 gigahertz, which is what determines the kind of maximal energy scale in the system. So all the dynamics that happens at frequencies below omega p. It's about 1 Kelvin. And the second observation important to my talks is that if you look at the size of this 20 gigahertz oscillator, it's really, really small, which means that there's something unusual about it. And what's unusual is that inductance normalized by size of these junctions is about 10,000 times larger than inductance of regular wires, which is just vacuum permeability. And this actually allows us to create circuits with parameters that you just can't, or well, actually you can create using regular electromagnetic structures. And then I'm going to talk about not a transmon qubit, so I need to tell you what a transmon qubit is. you basically take that junction and you shunt it with a capacitance. That capacitance could be made in the form of this antenna that is quite large. You can probably see it with your bare eyes, invented by this lady, whoever she might be. And that reduces the 20 gigahertz resonance to about 5 gigahertz resonance, which is a lot more convenient for the measurements. And the important thing to understand is that this transmon qubit is actually very, very useful, can do a lot of things, but it's not a true two-level system, because you see, we're talking about oscillations in this weakly anharmonic system, harmonic potential. And so there are higher states. And for this effect that I'm going to present, this is actually crucial. Like the anharmonicity really makes the difference between effect and no effect. So we'll get to that. Just keep that point in mind. Okay, so I guess probably no questions about the circuit introduction. So now I'm going to introduce you the two main players in this experiment. So the first one is Fluxonium qubit, and this is a qubit that is very different from transmons in the sense that it has a much larger anharmonicity. So it's very different in that respect. It's not very different the way it looks like, because it looks like the same kind of antenna. There's a small junction over here. There's a charge on this capacitor N, which is the main variable, but it's also shunted by this loop, which is just right enough inductance. This loop is over here, which kind of creates a potential like this double well. And the lowest two states, they correspond to tunneling of phase or flux in this well. So that makes a relatively low transition frequency from 0 to 1, but then relatively high from 0 to 2 and from 1 to 2. So you can roughly think that you just took level 1 and kind of dragged it down compared to transmons. And this is a more accurate description of an example qubit, where we show frequency on the x-axis and the charge matrix element on the right axis, kind of, which shows you various transitions. So you see some of them are forbidden in this particular case because of the parity selection rule. The 0-1 in this particular case is suppressed but not forbidden, and etc., etc. And the way it's measured, it's the same way you place it in a cavity resonator. Here it's a 3D one, and just do spectroscopy. Now the important point, kind of technical point about Fluxonium, is that to get the kind of spectrum you need, you actually need a relatively large inductance, which is very hard. I would say probably, I mean, maybe possible, but just very hard to do it using like a regular coil. And so instead we just use this chain of Josephson junctions with the right parameters, such that they just act as a large kinetic inductor. And it looks like this. So so the anharmonicity of the Fluxonium is crucial, but it also needs to be coherent, because you'll see that many body effects, they don't really show up if the qubit has is too broad. So let me review very colloquially the current status of Fluxoniums. So you see, in 2013 there was this summary of coherence times of qubits, and I guess all the advances have been placed on this plot where you show qubit lifetime coherence time on the y-axis and the year of production on the x-axis. And let's look just at the red dots. This is sorry, at the I guess it doesn't matter. Let's just look at these dots, and you see that they kind of grow exponentially. So we call it Schoelkopf's coherence law, by analogy with the Moore's law, that coherence time doubles every certain period in time. But it seems like this law has been in trouble lately, because the coherence time of qubits doesn't really grew that far beyond 100 microseconds. And so this Fluxoniums that I showed you, actually, in some sense resurrects the Schoelkopf's coherence law, because you see the latest coherence time exceeds 1 millisecond, and then you feel like, look at them. I made a mistake. I should have used this as blue points, because this was supposed to be T2, not even T2 actually, T2 star, but here it looks as it's T1. So sorry about that. Somehow in my head, blue is always T1 and red is always T2, but in this particular paper, they did it the other way around. Sorry for the confusion. In any case, so the T2 went that high, and it's not only the T2 is high, you can also do very high fidelity operations, so which means that this high T2 is real. And you can read more about this in this preprint. I'm not actually going to discuss this, but I just want to point out that this is where the fluxoniums are. And some of you are probably interested if you can do 2-qubit gates on these qubits, and the answer is yes. You just put them together like this, and our latest result is that you can do pretty good 2-qubit gate fidelity. It's this recent paper by Quentin Fischel. So those of you who are interested in this sort of topic, you can check out that work. And but again, for me today, the most important thing about Fluxonium is that it's a coherent 2-level system. Okay.
Vlad, maybe a quick
yeah.
question on the previous slide before we move on. Just out of curiosity, for those two transmons, the junctions seem to be aligned for some reason. Could you comment on that? The sites of the two.
Oh, you mean here?
Loops. Yeah.
Here.
That's right.
Yeah, that's that's because we wanted to use one coil to flux bias 2 qubits. And so the idea was you want to make their loops relatively close to each other. That's the only reason for this, actually. It actually worked that well. It works. It works from time to time. It doesn't always work. But that's what happens when you're trying to be cheap and save on 2 coils. Right. So the second player in this in the construction of this many body states of radiation is radiation. So let's make the Fabry-Perot. And so the way we make this is a bit unusual, but you will actually see right away why we're doing it this way. Is we use slow one-dimensional photons, which are hosted by a telegraph transmission line that is made out of just 2 very long chains of Josephson junctions separated by about 5 to 10 microns. Because you can model this structure just as a telegraph. There's some inductance per unit length, which comes from the Josephson effect, and there's a capacitance per unit length, which is just electric field between the wires. And not surprisingly, because inductance is about 10 to the 4 times larger than the vacuum permeability, you slow down light by about a factor of 100. You also get a higher impedance, but that's actually not so important here. And I also have to, I guess, for the completeness, introduce you to this notion of fine structure constant, which is a dimensionless quantity that enters in various expressions for the coupling constants, and it's just a ratio of the impedance, wave impedance, to resistance quantum. Here, 6.5 kilo ohms. To actually make a Fabry-Perot, what we do is we just make it a finite length. We put a short circuit on one end, and we couple some antenna on the other end. So you can think of the short circuit as a perfectly reflecting mirror, and the antenna as a weakly transparent mirror that allows you to couple radiation in and out of this Fabry-Perot. The aspect ratio is actually quite remarkable. You can basically have about 10 millimeters long. You can actually see it here on the chip line that contains about 30,000 to 50,000 junctions. It's actually not that hard to make. It also proves that the junction fabrication process is a very correlated process. Like you basically have either all are failing or all are working, something to kind of get out of this. But really, for us, it's just a very compact Fabry-Perot. And when you do spectroscopy of this, you can see all the modes starting from n equals to 1, 2, 3, 4 is 41. The spaced by about 100 to 200 megahertz. That's a kind of a convenient range, such that in the kind of 10 gigahertz window, you get approximately 100 modes, which is, our goal, because we want to make something that you won't be able to simulate on a classical computer. There's this, the other thing why the compact photons are important is because you see this 10 millimeter long line could be actually placed in a relatively small box, and it has no metal around it. So the electromagnetic structure of these modes is very, very pure. It's literally two wires suspended in vacuum. And that helps a lot, actually, because, that reduces disorder. Okay, so are there any questions about this structure?
Yeah, it's a very nice structure. Maybe a quick question. So the way we should think about this electrically is that you have, in each of the wires, you have some inductance and capacitance along the line, and you have a capacitance from the top wire to the bottom wire that's direct as well.
The first capacitance is irrelevant. Only the second one. That's so really, you can think of this thing that looks like a rail track. Just think of it as a wire. Don't worry about some grain structure. It's we're working at wavelengths which is much bigger than the size of the junction, so it really just looks like a wire. In fact, I mean, there is some effect of the plasma frequency, but it happens around, as you approach 20 gigahertz. So you can for now just think of it literally as just a compact telegraph line where photons are slow, and as a result, the device is just small.
I see. And so could you tell us about the sort of relative capacitance value between, say, the one that goes vertical versus horizontal? Say the little self-capacitance of the junction is much smaller, much larger than the one between a junction at the bottom, junction
Right,
island at the bottom versus the top.
Yes. I'm not sure if people can follow this without a schematic. You see, I guess here I'm ignoring the capacitance, that oxide capacitance of each junction, because I work at a frequency which is much lower than the plasma frequency. So you can say that the current prefers to flow through inductor, because low frequency currents always wants to flow through inductors, not through capacitors. Now, in between the chains, there is no inductor, so the capacitance is important. And this is the bare kind of the minimal model, which is exact in the zero frequency limit, but it's pretty good, up to about 20 gigs. And actually, the capacitance that you put across the junction is much bigger than this capacitance between the wires, which may confuse you, because they say, well, why don't you neglect the bigger one? Well, because the bigger one is shunted by a short circuit.
Okay.
I tried not to confuse you, so it's all Zlatko's fault.
My apologies. Yeah, that's very interesting.
But I'm going to instead confuse you in a more. Any more questions about it, maybe? Huh?
Yeah. I guess it's interesting, because with these junction arrays, of course, there was all of this discussion and long kind of history of minimizing the field lines that leak out of the structure to anything else. You want to confine them between the junctions in the wire itself. But here you're actually exploiting those extra field lines that are normally going to ground or something to form this resonator.
That's right. You can imagine some kind of a cloud of electric field, which is just kind of rolls around this wire, well, with this telegraph. And you see this cloud is going to be rough at some distance comparable to the wavelengths away from the structure. So it's still pretty far away from the copper box wall. So, in that sense, it's still a pretty good waveguide. It's not, it is not what I would maybe use for to read out qubits because because you see, I had to work hard to get to remove everything else from the chip. But in this particular case, that seems to be the most accurate solution. I'm gonna
Are the junction is the junction array dimensions of the junctions themselves, are those pretty typical, like relative to what you would use in a Fluxonium superinductance? Or are these?
Yeah, these are basically Fluxonium junctions. This is just that inductance just extended, by a factor of 100. So now let me confuse you a little bit more. It's a sidetrack, but I just couldn't miss it. Imagine, I should have asked me this question. So suppose you ask me, did you actually measure resistance of that thing before you, because you can imagine doing this, right? I mean, you can just wire bond the two wires and just measure the resistance. Well, it turns out that I did, and the resistance of that thing in the previous picture is 1 megaohm at the 20 millikelvin temperature. Anyone want to guess? At
DC, right?
At DC, at DC resistance, just not DMM, but something lock-in, with a lock-in. And yet in the left plot, I'm showing the quality factor of these modes, not in the full frequency range, between 5 and 10. So you see, it's around like 10 to the 4, maybe a few 10 to the 3. So it's not it's not an amazing resonator, but it's a pretty good, it's a high Q resonator. And yet the wires have megaohm resistance. So to kind of make a comparison, imagine a USB cable, which is basically what a telegraph transmission line is these days, and imagine a USB cable working, in case it has a megaohm resistance. So this is what happens here. I guess some of you may guess why. The answer is that well, it's actually an insulator. Because as you make a long chain of junctions, you're going to make an insulator. In fact, there's a theorem that one-dimensional superconductors kind of not exist. They turn into insulators. But this particular one, there's a quantum phase transition, and when impedance is sufficiently high, is going to become an insulator. And well, that 1 megaohm thing doesn't really prove that it's an insulator, but it definitely tells you that there is something wrong with superconductivity in that device. And there is a nice so we wrote a paper about this in 2019 because we thought it was so amusing, and our theory colleagues actually came up with a nice qualitative explanation, which basically says that if you look at in the low frequency limit, these as you slow down photons in the superconductor, that comes at the price of quantum fluctuations of the phase, and that in turn destroys the phase order. So you're going to have to make an insulator, but these quantum fluctuations, they always have this property that at higher frequency, they become weaker. That's called renormalization group kind of phenomenon. And so if you probe your system at a high enough frequency, an insulator becomes a superconductor. And as you make it more and more insulating, this parameter, actually, this fine structure constant actually is what controls the transition. Even at a fine frequency, you're going to make an insulator. But you can have this regime where impedance is very high, speed of light is very low, and your insulator behaves like a superconductor. And for those who kind of want a more, humane explanation, just check out these funny frogs which can actually run on water without sinking. It's basically classical interpretation of, it's incorrect to interpret quantum effects classically, but at least you can remember it like this. Like essentially, as the frog swings fast through water, the water becomes hard, and hence provides reaction. So likewise, when you probe an insulator with a high frequency, the phase becomes stiff and provides reaction, which is inductance. So our Fabry-Perot has to be made out of insulators, but it still works. Okay, that's my sidetrack.
That's very cool.
And finally, we arrive at the system I wanted to describe today. Is if we now attach that Fluxonium qubit at the end of this at the end of this Fabry-Perot that is also made of chains. So yeah, as you see, the Fluxonium loop is here, and it's the same junctions as in the rest of the chain. And the coupling here is inductive, so it's not a conventional Fluxonium that we use for quantum computing. You see there's no antenna for the small junction. In fact, the capacitance of the small junction is just the oxide capacitance plus whatever comes from these small leads. And then the coupling to the line is controlled just by the number of shared junctions between the loop and the transmission line. And this is the Posar style book circuit schematic. So you have this line with impedance Z and speed of light V and length L. And we can model antenna as a capacitance and a port, which is not exactly correct because that capacitance is going to be frequency dependent, but it's not, it's not going to change things too much, so it's okay. And then the qubit you couple as this thing, so you have fraction X of the total inductance short circuits the line, and then 1 minus X is over here, and then you have a junction. So you can think of the qubit as flux tunable, so we apply some flux and then it swings the transition kind of like this. Don't really need to worry about the details of it. The minimal frequency point corresponds to half of flux quantum, but again, it's not super important. And this X parameter is what controls at least the nominal coupling of the qubit to the line. For example, when X is 0, you can say with certainty that Fluxonium it does not talk to the modes of the line. So and this is the system that I had in mind during my introduction, using the cavity QED and abstract analogy. So let's look at some data about it. So I'm an experimentalist, by the way. So I usually don't discuss anything before I've seen the data. And the data looks like this. So I sweep flux and I look at all these resonances of the Fabry-Perot, but now they're going to be flux dependent, and I'm showing you some regions, and well, I guess you got to be able to zoom in on your screen so you can believe me that underneath the black dots there is data, and you have these resonances. And honestly, it just looks like this picture that I showed you in the beginning. So you take mode number 43, and it looks like there's a qubit transition crossing it, so you get some vacuum Rabi splitting. Oh, sorry. Here we go. Zoom in. And in fact, let me give you some numbers. So you see this vacuum Rabi splitting G43 for the mode 43 seems about 15 megahertz. That's not a very large splitting at all. And the spacing between the modes is around 180 megahertz, and actually the frequency of the qubit or this mode is around 7 gigahertz. And then as I tune flux, I cross the other modes, and then here I reach the sweet spot, so I kind of turn back. Okay, supposed to be an easy data to see, and in fact, Andrew Hauck's group back in 2015 actually already did this experiment using a transmon and a very, very, very long transmission line. That's actually pretty awesome what they did. I guess you can't really see the scale here, but the length must have been something like 1 meter of that line. And then as you sweep flux, you basically see the same thing. So these are all the modes of the Fabry-Perot, and in fact, the mode spacing here is 100 megahertz, actually about maybe twice smaller than in our experiment. And then as they sweep the transmon through these modes, they see these anti-crossings. And in fact, this is quite a high quality data, so you can actually you see the spectral lines, very beautiful, very clean. It's just literally a vacuum Rabi splitting of a qubit with one mode at a time. Okay. So, any questions about this data? Andrew's data?
No, I think so far so good.
Great, because if we zoom in our case, we see something beyond just the vacuum-Rabi splitting. We see, so this is the vacuum-Rabi splitting, you know, the big one, but then you see there's something else. And it's actually not small. We can certainly resolve it within the line width. And then there's this, and this, and this, and actually this. Well, maybe this last one, the last two you could have discarded as some glitch, but we know it's not a glitch, you know, from analyzing, you know, a lot more data. So obviously these qubit photon hybrids, qtons and phobits, other people call them polaritons, interact with something which is just a part of this system. It's not a two-level system or any kind of junk because it's clearly flux dependent. And this has obviously never been predicted before. I don't think anyone has heard of this kind of prediction to see a vacuum-Rabi splitting to be corrupted with some other splittings. It looks like there's something else. It looks like, for example, black box circuit quantization doesn't really predict anything like this. So it looks like we found a new effect that needs to be explained. In particular, what are these states, and what determines these splittings? And I remind that the coupling is not that large, because you see the vacuum-Rabi splitting with each mode is only, is only, it's like one fifth of the mode spacing, maybe even 1/10. I deliberately picked this device to illustrate this effect. So now let me tell you what we had to do.
We move on. Quick question. The dotted lines, I guess the theory that's overlaid on the spectroscopy there, how is that produced? Could you say something more about that?
Yeah, it was produced the same way, I showed in my very first slide. You just basically consider only one photon states, and your qubit hybridizes, with this one or with this one, with this one, and you can just include all of them. So the bottom line is that you need to diagonalize a matrix roughly 50 by 50 to get these lines. So you see, you get you get a qubit, either qubit excited or one of these modes excited, and then you get the coupling. Okay.
I see. Okay.
Like
it's from a numerical diagonalization.
Yeah, by numerical diagonalization. Yeah, it's a classically easy problem because they're not. There's only one photon in the system. I can explain more details about it actually, maybe after the talk, because actually this procedure is important. It actually gives us parameters of the qubit, and what helps a lot is because the coupling is very small, you kind of know that you can almost kind of extract the qubit frequency without even matching the full spectrum, because it's pretty clear that this is your qubit. Right. So now let me tell you what I've learned by trying to actually explain the splittings. It's my COVID project actually.
Oh, and sorry, one more question, Vlad.
Yep.
From the audience here, do you see additional peaks at low power? I guess what happens perhaps as a function of your spectroscopy power. Is this some super high power effect, or if you?
No. It's on the contrary. This is the super low power effect. So all this spectroscopy is done with a lot less than one photon in the drive to probe this, and so this is absolutely single quanta regime.
Awesome. Great, thank you.
Yeah, which is an important point, because you see, I want to probe states involving very, very small number of photons. So I cannot probe them with a large drive because that's not going to work. And and as a result, it's kind of like, you probably know, some of you know, that if you want to probe vacuum-Rabi splitting, if you drive it very hard, you're not going to measure the regular vacuum-Rabi splitting. You're going to measure some kind of a mass. And so likewise here. So this has to be taken with a very low power. Okay, now let me tell you what I've learned trying to explain this this data, and I learned actually quite a lot. So I'm kind of excited to share this with you. So basically, the problem really is that the qubit is really not a harmonic oscillator, so you cannot apply black box quantization to it, and you need to find some other reasonable model. Now you take the what you can do is you can take the transmission light part, and you can model that as a collection of harmonic oscillators, let's say like this, as a parallel combination of series LC oscillators. It's called Foster decomposition. It's not the only decomposition, but it's, you know, the one we chose to do. And by having infinite number of these oscillators, there's a theorem that says that it, you know, by choosing also the right Li and Ci, you will get exactly the same impedance between these 2 points that is attached to the qubit. And for the simple case of non-dispersive open-ended line, the impedance is simple, so you need to match the Foster impedance and the real impedance, and from that you get, it's kind of funny, so you see the inductor is actually constant, but capacitance with the mode drops as 1 over this I minus 1/2 squared. So okay, so at least you get a circuit model. Then you can write a Hamiltonian. And this is where the first disturbing things comes out. Usually we like to write circuit Hamiltonians such that the capacity, you know, we use phases across the capacitors such that the kinetic energy is, you know, is easy, diagonal. And then we do Legendre transformation and get, you know, this Hamiltonian. So this is, you know, what one is tempted to do first. And then you're going to see that you have a Hamiltonian that splits into atom, modes, and interaction. And the atom is basically Fluxonium Hamiltonian. You know, there is the C, J, L term. And there are modes, you know, with some frequency. And then there's a linear coupling of phase of the across the junction to these modes. It looks a lot like just inductive coupling, you know, flux coupling, right? It's inductive coupling, so you couple via the phase variable. And then you can plot these coupling constants G as a function of mode index and for various values of X. And you immediately find something very disturbing about this model. So the first thing is that the coupling grows as you go as you go to higher modes. And well, then the question is, well, what mode number do I take, right? Because how can I justify truncating if my coupling keeps getting larger and larger? So this particular case is made for the case of 10,000 modes. Even more disturbingly, if you look at the value of this G1, let's say, as a function of the total number of modes that you took into account in calculating G1, it actually depends on the number of modes. So you see, as you vary here the total number of modes that you took into account, G1 is as a weak, but you know there's a dependence, and in fact, as you make the number of modes larger and larger, you're gonna get some dependence on the basically on the cutoff, which is not great because then you don't know what to do, what end to choose. Even worse, if you look at the inductive energy of Fluxonium, it's not given anymore by just L, but it's some complicated function of N, and it's drawn sort of over here, which basically says that not only the atomic parameter depends on the number of modes you take into account, but you know the couplings depend on the number of modes you take into account, and then whatever you do, the couplings grow for higher modes. So it seems like the worst possible case to do numerical computations where you need to truncate and you just don't know how. Okay.
I have a couple of questions here. Oh, sorry. Maybe finish the note here.
Okay, let me finish by acknowledging that we're not the first who encountered this. So in case of transmons, there were these 2 papers in 2017, which I think pointed out exactly the same issue, that that you know, for transmon capacitively coupled to a transmission line, the common way of writing the circuit Hamiltonian produces exactly this kind of effect. And these 2 papers found interesting ways to go around this, but I think a black box circuit quantization still kind of does the job even better, because it says, well, you don't need to worry about all these divergences. You know that your qubit is just seeing an impedance, and it finds a recipe of how to write down Hamiltonian just in terms of the values, the properties of that impedance function. And then, of course, everything is sane and clear. And unfortunately, that doesn't work for us because we don't have a weakly anharmonic oscillator. And so all these recipes do not work. At least we couldn't see them. So we need to do something else. Now, Zlatko, go ahead and ask me before I go.
Yeah, and maybe you somewhat anticipated that with this, so I'm not sure what's going next. But I was going to say, this looks and sounds just like the A-squared diamagnetic contribution. And I think when you account for the sort of self-energy of the coupling term and its effect on the renormalization of the normal modes of the transmission line, right? Then you get this G that decays with increasing frequency, no?
No. So this model is actually correct. There's no so basically this Hamiltonian and the plotted parameters make no approximation with respect to this circuit. So all the terms I've taken into account. I will give you a hint of what's wrong. So what's wrong is that you see you get problems in multiple terms of your Hamiltonian. So your L goes nuts, and then your G goes nuts. And basically, the reason why the Hamiltonian still describes the real physical system is because kind of the nutsy things about these two terms cancel each other. But there's no way you can, at least I couldn't figure it out in this particular, choice of variables. But there is a way. So basically, this is not an approximate Hamiltonian. This is a correct Hamiltonian according to circuit theory. It's just that it has several misbehaving terms, and you can hope that the total thing behaves because there's some cancellations. It's just that you can't track it down like this. Like Hakan's guys, figured it out, but I think they did it in a special case, and which we can't really apply here. And so we were looking for some other solution that would be applicable to nonlinear systems, and we found it. And it's really, it's going to blow your mind. So what you do is you make a gauge transformation to this Hamiltonian, which I cannot write down because it's too complicated, but I can show it. And you need to simply swap L and C like this. So you see now the phase is across L and not C. And then you just, you crank the circuit quantization machine. And then what you're going to get is that in the atomic part, the inductive energy is no longer renormalized or anything. It's just given by the inductance of the loop. So your atom part just doesn't depend on the number of modes you take into account in the system. And the coupling is now not via phase, but via charge. So you get inductive coupling of a Fluxonium to a transmission line, and yet the variable that couples is charge and not phase, which might sound weird, but actually, if you think about it, there's nothing wrong with it because it's like coupling via momentum or coupling via position for an atom to the field. And then if you plot this charge coupling constant as a function of mode index, you see that they all drop at high energies. So they don't grow anymore. And so we solve the mode independent atom parameters, check. Coupling vanishes at high energies, check. And then this plot doesn't really depend on the number of modes you take into account, as long as this number is basically, larger than 100 or so. So basically, the model is cutoff independent, which is what Hakan really wanted to achieve with the transmon, and he basically found that there's there's a natural cutoff, and I suspect something like this happens here, except that all we did is just did a gauge transformation and move the coupling into the charge term. And the only cost of all this is that now the coupling is large at low frequencies, right? Because you see, G is kind of larger at low frequencies than at high frequencies. And it turns out this is what really is making the new physics to come out. Now, any questions about this charge gauge thing?
Yeah, maybe a quick question. What do you do with the And I guess maybe in your Lagrangian or Hamiltonian, when you do the quantization, you have this non-dynamical node, at least in the picture here, where there's no capacitor touching it. So I think you have 1,0 mode there. Yes, that's one.
The phi m. Oh,
Yeah.
nice! You observed it. Yeah, you see, we deliberately, I deliberately painted it in gray, not in red,
Oh,
exactly
yeah,
to
that's
say
very
that.
nice. Yeah.
Yes, you have great eyes. Okay, so no. So the way this works is that basically phi m is not a circuit variable. It's actually constrained because by the
Right.
current conservation, and you just have to eliminate it when you define your generalized variables. So I guess we can write the constraint, but it comes from the current conservation in this node.
Yeah, it's a holonomic constraint. But I guess, and you do that in the previous slide as well. You take care of that.
Yep.
Here.
And it's a different constraint because it's expressed via different variables. So that's the kind of the only annoying algebraic part that you need to do to get the Hamiltonian right.
Yeah, it's quite annoying.
But okay, so fine. So we found this model where at least the atom is not weird. The coupling looks good. At least we can truncate it. So can it explain the data?
A quick question, Vlad, before we move on. So in this model, I guess on the previous slide and on this slide, the frequencies of the modes, are they evenly spaced, or are they sort of the solutions to some transcendental equation?
We find them as solutions to some nasty equations, but they always come out as evenly spaced within the numerical accuracy of the So maybe there's a way to do it. Maybe there's a way to actually do it analytically. We just didn't try it. And the reason we didn't try it is because in the experiment, the modes are not evenly spaced because of dispersion and disorder. So this model is actually does not require even spacing to begin with, because you see you can have some effects in your transmission line that make mode spacing not equal, and this Foster decomposition perfectly takes into account. And then the idea is that you really use it as an experimental parameter because you measure those modes. So that's pretty much all you know.
I would expect the mode spacing to not be equal if you have a strong coupling. Maybe if it's very small coupling, it looks equal, but wouldn't the coupling sort of change the mode spacing?
No. The only thing that it does, it can change a little bit the effective speed of light. But I don't think even that happens. I can look into this. I was curious about it myself, and I found that essentially no matter what you do, basically both in the charge gauge and in the flux gauge, they actually these frequencies do not really change, which means that there must be some analytical way to show this, and I didn't yet, because again, in reality they're not evenly spaced. But for this simple model of a non-dispersive line, it looks like they are evenly spaced in both gauges.
Yeah, that's very interesting, because my intuition tells me that you have a transmission line, and on one end, the boundary condition, rather than it being open or fixed, now has this inductive behavior, and so it depends on frequency. So each mode will see a different effective boundary condition because it depends on frequency, because it's an inductor. So I would have expected them to change, but maybe there's some
no, that effect is actually very difficult to spot. It's actually very small. You'll be surprised how small this effect is. So maybe this effect takes place, but maybe this effect takes place, but it's very, very weak.
Interesting. Yeah.
That,
I'm quite into it, because we just put out a paper where we had like this effect renormalize the mode by a gigahertz. So it's for me, it's but it's a totally different system. So yeah, very different.
I see. Okay, that's good to know. Yeah. But again, remember that these modes B are not yet the modes that you observe in the experiment, because there's also coupling. So that's why it's really only the eigen one photon eigenstates. That's really the only thing you should be worried about, and those of course know everything about this qubit.
And is G here comparable in size to F, or G is much smaller than F, or comparable?
Well, that depends a lot on the parameters. So for example, you see, if you take the blue curve, obviously F is changing by a lot.
Yeah.
And if you look at the high frequencies, G over F is always very small. I'm going to talk about this just in a slide. I don't actually have that many slides left, but we're coming to sort of, the climax.
Yeah, perfect. We're at the 1 hour mark, just so you know.
Yeah, I know. But we're talking, so I need maybe another 10 minutes. Right, and you see, if you compare the blue and the brown curve at the same mode frequency, you can get a variation of almost 2 orders of magnitude, which basically, the point of this slide is to show you that, well, you actually can get quite a diverse values of couplings, not only as a function of frequency, but also as a function of circuit parameters, the given frequency. And these curves correspond to realistic fluxonium coupled to a realistic line. And I should also say that this kind of high impedance thing is not very important. You can actually get the similar similar models for a regular, like, 3-junction flux qubit coupled to a low impedance line. It's actually yeah, so the high impedance part is not so important here. It's just that it's important to make the device compact for to get the measurements possible. Okay, and now we're coming to the really hard part. Sort of the many-body physics begins. So let's look. So now we need to truncate fluxonium to a 2-level system, because Fluxonium Hamiltonian is not a Hamiltonian of a 2-level system. It's a pretty complicated one, and we have no hope to really figure this out with all the levels. So we need to truncate it. And if you truncate it, you're going to get a Hamiltonian like this. So let me read it just on the top. I should have staged this slide. It didn't occur to me. So just don't read the bottom yet. Don't be scared. So you see, we split fluxonium transition into sigma z and sigma x terms. So you can think of sigma x as something proportional to phase operator. And so, as you kind of apply flux, Ex changes with flux. And so while Ez is a constant, so this is the qubit. And because it's coupled via charge, so we need to introduce coupling to the B modes using sigma y. And then we get this matrix element of the Cooper pair number operator kind of coming in here. And that thing is just a constant. It's less than 1, it's about 0.3 in this case. So just kind of don't worry about it. I write it down just, for completeness. And then we have the modes. So this Ex is our tuning knob. So when we tune flux, we tune Ex in this Hamiltonian, nothing else, more or less. So now the difficulty of this Hamiltonian is that G gets really large at low frequencies, and so you get and this is not great for many reasons, because it introduces displacements to the low frequency B modes, and one has to be very careful treating that. And so the trick that you do is called a partial polaron transform. So what you do, you introduce the bosonic field B, which is just a superposition of the operators which are conjugate to the field that couples to the qubit. So see, here's Bi minus B dagger, and here you put Bi plus B dagger. And you use this carefully chosen constant alpha I, which is going to be very important, the value of this alpha I. And it's literally just the ratio of the coupling constant to the frequency. So you can view it as a dimensionless coupling. And then you sum over all the low frequency modes, and I'll tell you what qualifies as a low frequency mode, but basically up to some max mode. And then you form this polaron transform operator. Basically, when you apply this operator to this Hamiltonian, what it does, it kind of destroys this coupling term for low frequency modes. It kind of annihilates it, but as a result, it does something nasty to sigma z and sigma x. And so when you do this, you arrive at this Hamiltonian. And so to help you read this, I marked in red the low frequency modes, and in blue the high frequency modes. And so if we just read the high frequency modes part first because that's easier. We just get the mode starting from I max plus 1 to infinity. And then we get this kind of linear coupling of sigma y to this high frequency modes. And that blue part is basically what governs the hybridization of the qubit with the high frequency modes, which is exactly how the dotted lines were produced, Zlatko. So you asked about those theory lines. So it's just a diagonalization of the blue part of the Hamiltonian, nothing else. And you do it in one photon basis. It's just like a 50 by 50 matrix. And then we get low frequency modes, the red. So we have from 1 to I max. These are the modes. And then we get this really unusual coupling where you get sigma z times cos b and sigma x times sine b. And then here you get a different combination. And you can imagine that as you tune flux, you change EX and expectation values also of sigma x and sigma z. So that thing is actually quite flux dependent. And so what this term does, it couples, so the qubit on one hand couples via the charge variable to the high frequency modes, but then it also couples to the low frequency modes, and this coupling is very nonlinear. You see, it's cos. And when these alphas are large, it's a really cos and sine. You cannot expand them. When alpha is a order unity, you have to take into account all the terms in the cos and sine. And I want to point out that this form of Hamiltonian has been discussed somewhat phenomenologically in this Nature Physics paper by Omar Di Stefano, where they were worried about, okay, how do you truncate a qubit to a two-level system without violating gauge invariance principle? And they actually arrived at a very similar Hamiltonian, except they didn't do partial polar transform. They did a full transform, so they just didn't have the blue part. So they really just had that. And it was more like a guess, like they didn't even derive this Hamiltonian. They just found that that's the most gauge invariant one, which is a good sign for us because not only this thing should be the most gauge invariant, but it also gives us the right answer, as you'll see. Now, this is probably very complicated, so I made a little graph to explain exactly what's going on. So basically, because the qubit operators talk to both the blue B operators and red B operators, you end up having a process where a state that involves just a photon in mode K can couple to a state which involves one photon in mode I, which is low frequency one, and one photon in mode K prime, which is close to K. And this is really, really unusual because the coupling alpha 43 at the qubit frequency is very small, right? That's why we get like individual vacuum Rabi splittings. And you would imagine that, oh, I'm in this like possibly most boring regime. But the alpha for the first mode here is about 3. So, which means that these cosines and sines are really, maximally nonlinear. And in fact, that produces, that basically produces the coupling of the high frequency modes to the low frequency modes. And you can view it as an elementary many-body process. You can have K into K prime and I, but you can also have, so sine is responsible for the 2-photon, 4-photon, 6-photon states, and cosine is responsible for 3-photon, 5-photon, 7-photon states. And this width of the blue region is, roughly speaking, the overlap between photon phobit Q-ton hybrids at high frequencies. And in our case, the overlap is very small because alpha 43 is very small. But because the alpha is very large at low frequencies, even despite the small overlap at high frequencies, you get a observable coupling at low frequencies. And when you calculate the matrix elements between the relevant 1-photon, 2-photon, and 3-photon states, you reproduce the spectrum without adjustable parameters. And let me now explain exactly what these states are. So you see, we call these these kind of simple one photon states, we call them polaritons just because it's a hybrid of a qubit and a photon, so we call them with p operators. So this kind of main line is just an excitation of polariton number 44, and this one is the polariton number 43. Here's the regular vacuum Rabi splitting between them. And this state is a 2-photon state that involves a polariton number 43 and one low-frequency photon in mode 1. And the one next to it is a polariton number 43, but 2 low-frequency photons in mode 1. So this one is mode 2. Oh, this one is mode 3. And the remarkable thing is that without really, we only use basically this left spectrum to extract qubit parameters, use that charge gauge plus polaron transform theory, and we get this splitting of 1-photon state and 2-photon states just right. And the crazy part is that if you try to do it analytically, you will find that this splitting, omega over here, it scales for this device parameters like alpha 1 times e to the minus alpha 1 squared over 2. And alpha 1 is about 3, so that exponent is very small, but alpha is very large. And so that's why you kind of get it resolved. And you see, if you make a mistake in alpha 1 by like 10%, you're going to be way off because, it's a sharp exponent. And somehow, we got it, which I think shows that this description of circuit description that I showed you is actually very, very accurate. So I meant to actually post this paper before my talk, but for various reasons didn't do it. So it's going to appear, but hopefully when it appears, you can watch this talk in reading it, and it will help you. Now let's see, Zlatko. So maybe I can answer some questions about this plot if there are any, and then I can show my conclusion slide.
Yeah. We had a question from earlier, and I assume the answer is yes. But the question was, do you see this do you see the same type of behavior of the lines at every level, at every crossing?
Yes, you can probably, maybe if you can zoom in, you can see some remnants actually in this data, because, it's the real data. It's just, so yeah, absolutely, yeah.
Mm-hmm. Right. I see. So then
and I want to stress once again that these splittings are impossible when your qubit is a transmon, because this theory that I showed to you, it really breaks down when your qubit is not a 2-level system. So that's why they have never really been seen on a previous multimode experiments on transmons, of which there have been plenty actually.
And can you comment on what are the parameters that go into this? What do you mean by no adjustable parameters again? I think I lost you on that one.
Yeah, so you see, you can look at sort of 1-photon spectrum, and from that you can extract actually qubit parameters pretty accurately. As I said, you don't even need to fit it. You just sort of see a qubit line. You can just fit to that. But you can improve the model a little bit more. You can just use the high frequency values of G's, basically. You see like this terms, like G's at high frequencies, like in this region where there seems to be just weak and boring. So, why not? And then you feed that, and you reconstruct the low frequency part of this curve using the circuit theory that I presented, because it connects these values to those values. And indeed, you find that you get the splittings just right.
I see. And is that by tuning? How does that work in practice? Like, do you have like L's and C's that you vary for your circuit model, and you fit the spectrum? Is that?
No. They're actually, the way you feed the spectrum, you see, you have it's better than this.
Yeah.
Because you have you only have
you have
wave impedance. You have wave impedance, speed of light, and length, and then that's the transmission line. And then in the qubit you have basically EL, EC, and EJ. Now we can extract a wave speed of light quite accurately from just the mode spacings, and we have a pretty good bound on impedance, sort of within 10%, also from the spectroscopy data. So in the end, there are only 4 adjustable parameters actually.
Yeah.
So you use So you use 4 adjustable parameters to get this spectrum, and then apply this theory to calculate the multiphoton couplings without adjusting anything. You plot it, and it looks like this. I mean, of course, if you superimpose, there will be some small disagreements, but actually, if you look at the formula, it's kind of hopeless because you have an exponent here. So I'm still quite I'm surprised that it works so well. Right, and I have to comment on this that you see this plot. Like for those of you who are maybe keen on high energy physics, this is actually nothing less than asymptotic freedom for photons. So you see. The way light matter coupling works, at least in circuit QED, you can't really see this in cavity QED, it's just too weak, is that if I didn't have any low frequency modes in the system, like suppose I just had some kind of a band gap between 0 to 2 gigahertz, then I would just see regular vacuum Rabi splittings because my coupling at the qubit frequency is very low. But when I have low frequency modes, I get this like bigger and bigger coupling because it's parameterized by alpha, and I get to see the coupling to basically to states involving low frequency photons, which I think for circuit QED crowd is very counterintuitive because we used to this thing that if the 2 modes are very detuned, just forget about them. Forget about it, and here you cannot forget about it. In fact, the low frequency modes are actually quite. You see this secondary splitting actually corrupts the first one quite significantly. So that's the kind of the cool new thing that that I found, and now let me give you my conclusions, because I think that that could have some future. So first of all, this picture kind of represents the main effect that I just described to you, that you have a coupling between a 1-photon state in a Fabry-Pérot resonator and a 2-photon state that consists of almost the same photon, just like a little lower frequency, and a low frequency one. Of course, in a real system, the degeneracy is not exact, but what happens is that as you tune the qubit frequency, you kind of tune the effective polariton frequencies too, and eventually you hit the degeneracy. That's why I see only one, that's why I can resolve splittings one by one, even though there are many body states. So in some sense, some disorder and dispersion in my system helps me to resolve individual many body states. And this splitting can be surprisingly high. Now, okay, so now my summary is that I've introduced you to this notion of many body states of radiation. These are not the only many body states of radiation, but I think these are the simplest many body states of radiation because they require very little energy in the system. I showed you a calculation-friendly light matter coupling model, which is somewhat counterintuitive because it says that an inductive coupling of a qubit to a line should be treated using charge. I showed you a new mechanism of photon-photon interaction that cannot be predicted using BBQ, and it is essential to have a 2-level kind of a strongly anharmonic qubit to see. This effect is vanishing as you reduce anharmonicity. Your homework is to figure out why did I call this talk quantum impurity regime. Those of you who are interested are welcome to write me about this, or wait until we get the preprint out. And finally, I want to conclude. So the reason I selected this talk for an IBM Qiskit talk is there was a reason for this. Is because I think the key application of this effect is that it's an example of a problem for a quantum computer that you can solve using an analog version of this quantum computer. Basically, you do the experiment, right? You measure the spectrum, you find this many body splittings, and I presented you the simplest case where the coupling at the qubit frequency was weak, and as a result, only few many body splittings are important. But as I crank up the coupling at the qubit frequency, there's going to be a lot more splittings. And simulating that on a computer is going to be a hard task. And I think it's an excellent problem to verify quantum computers, because if you have a quantum computer that can simulate a molecule, it's going to be able to simulate this thing. And this it looks a lot like bosonic kind of bosonic simulation, right? You just have a number of modes coupled to a qubit. And I look forward to, I guess the quantum computers growing to the degree that they can simulate the system, because then we can use sort of analog quantum computer to verify a digital one. On that, thank you for your attention. Happy to take any more questions if you have.
Thank you, Vlad, for the really nice results and awesome talk. Maybe just 2 quick questions, since we're 20, so, we're a bit over, but we had lots and lots of questions during the talk. Can you comment real quick on the coherence of the qubit in the system of the Fluxonium, and how is it impacted by the coupling to the line and so on?
Right. So you see, it's important to work away from the sweet spot to observe this effect, because you see, you kind of observe it as you sweep flux, and that modifies the transitions. And if you, I guess, Zlatko, you're familiar with this, you see we're kind of really far away from the sweet spot, where the coherence is just limited by flux noise and the sensitivity to the, basically by the inductance. And in this case, we typically get around a few microseconds of T2, just limited by really just 1 over a flux noise, which gives us line width of about, a few hundred kilohertz. And that's plenty to resolve these small splittings. If you do the same thing with a regular flux qubit away from the sweet spot, it's going to have a line width of 100 megahertz, so you're not going to see any of this, which is partly explains why in flux qubit experiments this effect has not been, noticed, so it's important to have a relatively high coherence qubit. It doesn't need to be, a millisecond high, but you do need to have a line with a lot less than a megahertz to be particularly sensitive to the splittings.
Wonderful. Well, seeing as we're at the extra half-hour mark, I think even though there were a few more questions, maybe we'll table those for next time we have you back, which we certainly would love to. Vlad and folks from Vlad's group, thank you for the awesome results. Also, thank you everyone for tuning in today, and for all the questions, and for the great chat we had today. Thank you, Vlad, also for accepting the invitation. Any sort of final things you wanted to mention?
Well, looking forward to the first quantum computers to arrive.
As we all are, indeed.
Keep it strong.
Keep it strong. That's great. Well, on that very positive note, folks, thank you, Vlad, for the talk. Thank you, everyone, for tuning in. And with that, we will see you next Friday at noon Eastern Time. And we look forward to seeing you back on the seminar.
Thanks, Zlatko.